So this is y equals ln of secant of ln of 11 theta. Now, all right, let's work it the way the book works it, and some of you like to work it, and you'll see why I don't like to work it this way. So I'm going to start with the inside and call that u. So u equals 11 theta. And then I'm going to call this piece v equals ln of u. And then I need more colors. Is that in here? You got, yeah, you got my color. All right, and so then this piece I'm going to call w equals secant of v. And then this piece I'm going to call y. Why don't I ever have enough room? Y equals ln of w. All right, so this is how most of you would break this down. I don't do it this way, but we're going to do it this way. So I find the derivatives of each one of these. The derivative of u is what?
11.
What? Oh, I thought you said ln. Oh, my blue's gone. Blue. All right, the derivative of v is? No, we ain't doing that. And what's the derivative of, come on, that one?
I thought you didn't like using prime.
I know, but it makes, okay, I'm sorry. What's the derivative of dw dv? dw? What is it? What? Thank you. Secant cosine tangent, and the derivative of y? And then, boys and girls, you multiply all these pieces. V tangent v 1 over w. And so then you start substituting. So w is 11 theta. V is ln of u. And w is secant of v. So we can get rid of that. So I have 1 over theta times secant of ln u is 11 theta. Tangent of ln of u, which is 11 theta. Be sure you do the sound effects. And where the heck is v? Is ln of u? But wait, there's more. And so the last piece, 1 over theta, secant. I think my problem with these math problems is I get tired of writing all this junk. Tangent of ln of 11 theta, secant ln of u, which is 11 theta. Maybe I got all the parentheses. And so I can see that that and that cancels. And so my final answer is tangent ln of 11 theta over theta. Okay, so this is where you're breaking down 4 functions. I don't like that way. And again, it's just because I'm lazy. Look how much you had to write. So if you like that way, stick with it. You just won't get to come to my parties because we don't do this at my parties. You're going lame. So my parties, well, I can't make that where you're going to still be able to see it. So I'm going to have y equals ln of secant of ln of 11 theta. And I think, Sarah, you said this is the way you like too. Don't yell at me. I'm going to white. I'm going to white y prime. My way is take the derivative of the outside, the log, 1 over, leave everything alone in the inside. I wish I could, well, I could do it, I guess, with this. So I took this whole derivative. The derivative of ln is 1 over the inside. Now I'm going to put my finger over that. That's not there, so I'm going to take the derivative of secant, which is going to be secant tangent, and leave the inside alone. Tangent. I don't know what happened with all my parentheses, but deal with it. That kind of made it look better, not really. That's why my parentheses are off. Is that what you were saying?
Yeah.
Thank you, sir. That's a theta, even though it looks like a 4. You're on your own reading my handwriting. All right, so I took the derivative of ln, 1 over that. I took the derivative of secant tangent, leave that alone, times, now I'm hiding this, and I'm taking the derivative of ln of anything, which is 1 over the anything. And then last, I'm taking the derivative of the inside, and I'm done. That's why I like this way better. I used less paper, and I didn't kill a tree. Yay! Yay! But, and some of you may still be staring at this going, what? If you are and you like that way, use it. This way is just faster, less handwriting, meaning I'm doing that derivative, I'm doing this derivative, I'm doing this derivative, and then I'm doing that derivative. Okay, I'm just not writing all this stuff down. And I heard somebody up above, say something about the derivative, which was very good that they said this. The derivative of ln of anything is 1 over the anything times the anything. Well, when you do it up here, you're not doing that. You're just doing, meaning up here, which wouldn't have been wrong to say that. I guess I can't say that. In other words, they were saying to do this times the derivative of the u. And that's okay. I mean, in fact, I like that you gotten into a habit of saying that. But so either you have to break things down like this, and Patrick likes X's because, well, that's A, B, C, D, E, F. I have to sing the song to get the order. So use whatever variables you want. But if you can see this way, then I would use it because as you see, it's faster. If you can't and that confused you, then just erase that from your notes and your brains and all that good stuff. All right, so let's get another class, so now it'll be recorded. I'm going to do something with 3.10. It's either one take home, which I'm probably leaning against because you guys all cheat and you'll all get the same answer. Otherwise, I'll have to do 40 different problems, and I ain't up to that. What I probably will do is kind of hint to you what the problem will be. And so that way, and you'll understand here in a minute, I could say, well, I could give you the same exact problem, but just change numbers. Okay? Otherwise, you're going to see some of these, wait till the baseball problem. All right, so what we want to do here is basically we have more than one variables, but one of the more variables. One of these days I'm going to learn English, that could be changing with respect to time, okay? And this is a perfect example. I have this balloon. If I'm pumping air into this balloon, so the rate that air is being pumped into this balloon, you agree two things are changing, the volume of air in the balloon and this radius here. So I have two functions that are actually changing with, and I call these functions because they are functions. The volume is a function of time, and my radius is a function of time. So all I've done is rewrote, and again, I would give you, if you didn't remember the volume formula for a sphere, I would have given you that. I just rewrote this and said, well, this function is with respect to time, and then my radius is as well. And so just cube that. And as always, these slides are all on. And so now I want to differentiate this with respect to time. So to be able to do that takes 2 steps, meaning that if I want to find the change in volume with the change in time, I have to find the change in volume with respect to the change of the radius times the change in radius over the change in time. And so now I just start plugging this stuff in. So in other words, this dv, dr, dt, I'm going to take this derivative. So I just brought this 4/3 pi out front. That's just a constant. Bring this 3 down and then subtract 1 times the derivative of the inside. That's that piece. Okay, so that's what you guys kept saying there. That's your chain rule piece. And so now I can just make it look a little bit better. I just canceled the 3 there, and that's all I did. So now it gives me an equation here that if I knew the radius, then I could actually get an actual value. And if I knew how fast the radius is, a value of the change in my volume. So we know the radius of the balloon, and we know the rate at which the volume is increasing. So now in this case, I can actually solve with how fast the radius is increasing. If I know my volume, I don't know what I did, and I know the radius of this balloon, that it's changing. So for example, if air is being pumped into this balloon at a rate of 5 cubic centimeters per minute, and I want to find the rate at which the radius is increasing when the diameter of the balloon is 20 centimeters. Let's go back to that formula, and the only thing to remember is the diameter. This is radius, so you have to do half, okay? And so this gives me an actual, tells me how my radius is changing. And so all I'm doing is coming up with a function here to be able to come up with that. Notice what I did is I did this kind of in, I know you hate when teachers do this, from this step to this step. I just simply solved this for dRdt. So that went over there, and that's why it ended up in the denominator. All right, all of these problems, and it's funny that when I was in school back when we rode dinosaurs, and that's what y'all think probably. I hated math, believe it or not. I think I told you guys. I mean, in high school, shoot, I was about boys. I could care less about math. And, and so then I got out of high school and, went on my merrily way. And then when I started going to college, I took college algebra, and I was a computer programmer. So I liked algebra because variables, that worked fine, but it's all right. But then I took a trig class, which is y'all's pre-calc class. And probably the best teacher I ever had. And we would be working a problem, and in pre-cal, you're all drawing, triangles and, unit circles and stuff. You would have a problem, and he'd walk by, he'd give everybody a problem, and he'd walk by. And I'd have my problem all written out, and he'd go, well, where's your picture? And I wouldn't have my picture. He'd take my paper and rip it up into shreds. I could have a whole page of notes on that, and he'd piss me off, But it got me to the point where this step number 1, I don't think you guys realize how important this is. And I see a lot of, people out in the real world doing this. We're going to build a deck. And I see them get a piece of paper out and start drawing what they want the deck to look like. The reason why this is so important in here is when you draw a picture, you're going to say, oh, that's a triangle. That's a right triangle. I know how to do that now. But if you kind of just look at the words, I think these are going to be very difficult problems. Very difficult problems. So draw a picture, draw a picture. Get your variables and constants. Again, I always find computer science students have no trouble with this because you're used to naming variables. You're in a perfect world in this class that we're going to be differentiating with respect to time. There could be other type equations out there than just these, but this is what we're doing in here. And then you want to write down any values that's given to you. Number 3 is most important. I see so many students don't even know what they're asking me to answer. There's, you're a math major. There's way too many words. I don't know what they even want me to find. So you want to figure that out. Write an equation that relates everything, differentiate the equation, and then evaluate with whatever values you're going to plug in. So if we have this hot air balloon is rising straight up from a level field and is tracked by a rangefinder 500 feet from the liftoff point, we're told that the elevation, at the moment the rangefinder's elevation angle is pi over 4. The angle is increasing at this rate, 0.14 radians per minute. How fast is the balloon rising at that moment? Again, I could stare at those words for 30 minutes and still don't know what to do. But if I draw a picture, little dude rangefinder here, and then a balloon and everything happening, is I say, oh, well, here's a rangefinder, here's an angle, here's the distance from the balloon, here's the height of the balloon. I can figure this value out. I can figure any of these values out because this is a right triangle. So this helps me see. And so I just start plugging in things that I know. So I know, I'm going to start plugging in variable names. So I'm going to let theta equal the angle in radians the rangefinder makes with the ground. I'm going to let this liftoff from here to here be y. Okay, so that's my liftoff in feet. My t, time is in minutes. It said to always use t. And then my x, I'm going to let be this value, the distance my rangefinder is from liftoff. Well, they give me that. This was given, back a slide ago in this problem, that this is 500 feet. And this is, again, going back into your trig class. So I'm given some information here. It says at the moment the rangefinder's elevation is pi over 4 and is increasing at this rate. How fast is the balloon rising at that moment? So I know, if you remember in the picture, and I'll bring it up here, I know in the picture, well, it's going to be the next one, that the y was the balloon rising. So that's what's changing, is the balloon's going up. And so that's what I'm trying to find. I'm trying to find that change in y over the change in t. I'm just going to label these. They told me the change in my angle. Well, let's write it mathy, because I'm going to have a math equation that I can write this down. They give me that. They give me this. Okay, so this information. And so how fast the balloon is rising at that moment, this is where I said this is what you want. How fast is the balloon going up? That was y on the picture, so the change in y over the change in t when my theta reaches that angle. Okay, so here is what's changing. The balloon is rising up, so that's what I'm trying to find. This is something I wouldn't have given you, and this is why you have to kind of go back and rely on your pre-cal days. If I have this angle, and most of you remember that whole SOHCAHTOA thing, is I probably wouldn't want to use the sine, because if I use the sine, that's going to be my opposite over my hypotenuse. That gives me two values I don't know. Okay, so I probably wouldn't use that. I remember the tangent is my opposite over my adjacent, and so what I'm going to eventually differentiate is y. So that's not too bad. This gives me an equation. And I just said I'm going to differentiate it with respect to y, so why not solve it for y? I wonder how many times I can say y. All right, so here is my equation. My change in y over change in time. This is what's changing. This balloon is rising. Equals, this is just a constant. The derivative we just said of the tangent is secant squared, and then times the derivative of the inside. So this is this implicit stuff basically, because there is no t here, so times d theta dt. And so now I start plugging in things that I know. I mean, you could have plugged them in before, but it's kind of nice to take derivatives with the variables left alone and then plug in the information. And then, of course, secant, well, some of you guys are just going to use your calculator, but of course with secant, you can do 1 over cosine, and it is squared. And all this out, you should get 140 feet per minute. But again, a lot of this is, one, figuring out, well, what is it even asking me to do? It's asking me how fast this is changing. This balloon is rising with respect to time. The change in y over the change in t. So I have to figure out a formula to be able to do that. And this one works so perfectly with the tangent, because once I saw there was a right triangle. Now, if you did not draw this picture, my guess is, I mean, I don't even know how I would know what to do without a picture, because I wouldn't understand that I have a right triangle going on here. So, I just try to sketch something of what they're even asking me to find. All right, another example. A metal cube dissolves in acid such that an edge of the cube decreases by this 0.7 millimeters per minute. How fast is the volume of the cube changing when the edge is 6.9 millimeters? All right, so how fast is the volume? So I want to know the change in volume with respect to, and you kind of start, that's kind of how you start these, the change in volume with respect to time. So if I want dv over dt, I apparently need a v, right? That's my function. So my function is my volume. This, I think most of y'all know this one, but this one I probably would have given you. If it's not related to pre-cal, I probably would have given you this. And what I want to do is I want to express this as a rate. So in other words, the time rate of the change in volume in terms of the time rate of the change in edge length, and then differentiate and plug in. So my change in volume over the change in time. I think, again, this helps. If you know what you're looking for, then you know right there means that's my function. That's my original function, is volume. So you would know the step before, what do I even need? And so then once again, if I'm differentiating with the change in volume over the change in time, what I mentioned up here, that's going to be found by the change in volume over the change in the edge times the change in the edge over the change. And so this change here, my derivative, v equals s cubed, is just 3s squared times that piece. And in other words, how fast is the volume of the cube changing when the edge is 6.9 milliliters and the metal cube dissolves in acid such that the edge of the cube decreases? If it, then it has to be negative. Okay, so they didn't tell you that. That would just be common sense. You got to realize that if this is decreasing, this needs to be negative out, and it would make sense certainly is getting smaller. Okay, so the volume of the metal cube is changing at this rate when the edge is 6.9. Okay, so this one didn't take a picture, right? I mean, I had a picture of a cube. It really didn't need that. But I really think when you're setting these up that you first need to, kind of figure out what are they asking me to find, and then that will help you with your function. Now, this one probably wasn't too bad. The balloon, I mean, I'm just thinking here, if I give you something like the balloon one in class on a test, you're already freaked out because it's a test. Most of you would take maybe 15 minutes on that problem, okay? And the problem is then we've got 9 other sections that I have to give you, and that's why I could give you this same problem here, but just change values. I could give you the balloon problem again and just change values. So that's probably what I'm going to do. So, does anybody know in Little League T-ball, is it the same distance or is it shorter distances? You'd think it'd be shorter, right? Yeah, it's been a long time since I've seen a T-ball field. So this one would be an example that I could change to a T-ball field, and you'll see what I mean here in a second. All right, so a baseball diamond is square 90 feet on a side. In other words, it's 90 feet from each base. So we could say little kids only run, 40 feet, whatever they run, 2 feet. All right, so a player runs from first base to second base at this rate. Okay, so this is the rate that he's running from first. At what rate is the player's distance from third base changing when the player is 45 feet from first base? So nicely, they give you a picture. This is my math lab one. Okay, if they didn't give you a picture, you should be able to draw a picture. I mentioned this in my other class. I did and I may even give you that one. I have a football one where it's basically the same thing. You have a player here and you have another player cutting this angle, and this guy's going this rate, this guy's going this rate. When will he tackle him? Which yard line? But the funny thing about it is when I wrote the problem, I wrote it up and I said, I'm pretty sure I used the word wide receiver and cornerback. And this guy came up to me and he says, well, I don't even know what that means. And first of all, you don't know football? But no, he was from another country and he didn't know, what a wide receiver, he didn't understand what that meant. So just remember, when you're taking a test, if there's any time there's a question like this, there could be somebody in here, I don't know, if you're from another country and you've never seen anything with baseball, that you don't even understand how to draw this out. So if I give you something on a test that's more like, well, you kind of would have had to know something about baseball to draw this, just come up here and ask me, okay? All right, so this one, so nicely they give a picture. Let's go back through all this again. So from here, first to second's 90. Here, second to third's 90. Third to home's 90. It says this dude has left first base and he's 45 feet from first base. So he's right there. He's running, this guy that's running right here from here now, he's running at this rate of 18 feet per second. All right. And again, they even labeled this, which is kind of nice. It says let x equal the distance the player is from second base. Okay, so he's here. That distance would be x. And once again, if he's running, in other words, this is the rate that he's running, x is decreasing since the player is running from first base to second at this rate. So in other words, this would be a negative rate. He eventually, hopefully. And so again, I see a picture and my picture says, ooh, that's a right triangle. And then I start going, well, but you did things with tangents and stuff. But I think about what they're asking me to find. They want to know, and this is why, I don't think I mentioned that, from the player to third base. They want to know how this is changing right here as the player is running. So my eyeball is going right there. It says, apparently I need something where I'm going to solve for y, because y is going to be my function. Okay, so I say, well, I remember this whole Pythagorean theorem deal. So in other words, I take my 90 squared plus x squared equals, I take the derivative with respect to time. All of these are with respect to time. So this is your implicit. This is 2y dy dt. That's just a constant, so that went away. This is 2x dx dt, because it's with respect to time. And then remembering, what do I want? I want to know the change in y. How is this changing with respect to, simply solve for it. And so again, I'm looking at this y. How is this changing when this dude is running? You can tell the y, that's going to change, right? And so that's what's changing, is that line. How is that changing? That's this here. So if you can at least figure out what they're asking you to find, you could work backwards and say, oh, I need some kind of equation for y. And you could have solved the equation for y and took the derivative of it. Okay? I mean, I just left it as y squared and differentiated, but you'd still get the same thing. All right, so now I just start substituting things that I know. So I solved this for dy dt. I know what y is, okay? Now I can solve this y squared for y. So I just simply plug it in. Again, this is a distance, so it's not the plus or minus square root, it's just positive. And so I simply plug that value. And then also, I know this distance x, because we said he left first base and he's gone 45 feet. Well, then all I have to do is subtract 45 from 90, so that means he has 45 feet to go. And this information was given, which is my change in x, my change in my player running here with respect to time. So I just start. So as you can see, the hardest part is figuring out, where do I even start? How do I come up with an equation for this? Plug in, and then of course you'll get. You're going to see here, all of you might be looking at this going, well, why did she leave this like this? I factored out, because then I can take the square root of 45 squared is 45. That still becomes 2 squared. There's just 1 there. Reason, as most of you are already used to this, that cancels that I did this the way my math lab wants your answer. They do not want it as a decimal. So that's the only reason why I didn't multiply all that stuff out. Okay, so this gives, So, good question. So if I'm not allowing you to use a calculator, I don't think any part there, most of you could have done that without a calculator. You were trying, weren't you? And so I would, of course, leave the answer like this. I might even just say, go through all the steps and just put the numbers in your formula and leave it like that. Yeah. Okay. Good try, though. Alex, you will be happy when somebody in my Monday class just bugs me all the time about a calculator. All right, so again, what could I do to change this? I could change the rate that the dude's running. Again, I could change the, from base to base. I will let you know, you need to worry about getting your homework done and all the other studying. I'll either send you something this next weekend, or I will just say, be sure you really, really understand the baseball problem. And then I'll just change numbers, okay, to see that you really, really understand it. But this isn't even. All right, at what rate are these angles? So you can see the angles are going to be changing as well. If this line is changing as the player's running, that's certainly going to change, and this is going to change. So I want to know at what rate the angles are changing, angle 1 and angle 2. And so again, I kind of look at this and I say, well, this angle here, if I'm looking at this angle, I remember my opposite over the hypotenuse. So I could write it as 90 over y. Again, I want to differentiate. I want my d theta 1 over dt. That's what I want. Why do I want that? I want to know how my angle theta 1 is changing with respect to time. So I would differentiate this. Sine would become cosine times d theta 1 over dt. This would just become, that would be y to the negative 1 if you bring it up here. So negative y squared, 90 stays the same, dy dt. And it in this, so that's what I'm going to solve for. So I'm just going to simply throw this to the other side. And then finally, once again, I go back and read the problem and say, but do I have things? And so if I look at this figure, I can certainly see my cosine. I can substitute cosine as x over y, because if I'm taking the cosine of this angle now, that's my adjacent over my hypotenuse, and so I substitute. Okay, so it's x over y, so I just flipped it. That, of course, is going to cancel one there. And then I go back and start substituting things back in. I know what my x was. I remember from before. We solved this. This was my change in y. This was the very first question that we did. So I can plug that in. And then, of course, once again, I can plug in my y value. And this would be, Eric, a good example. Just leave it like that. Okay? And so that way, that shows me that you've made it to that point. And now, of course, you start plugging everything into your calculator. But that would be, because I know that would be a question, well, how can we do these type problems without a calculator? I would just say plug in your values and leave that step alone. I mean, if you want to simplify, you can, but otherwise, you just leave it like that. All right, so I will leave it up to you. And again, I give you the answer, but again, this could be show your work that make you do this to do the same thing with theta 2. I mean, the nice thing is you're going to just start out with the cosine instead of the sine, okay? And then differentiate with respect to time, and you should be able to get that answer. All right, will this problem ever end? The player slides now into second base at this rate. At what rate are the angles theta 1 and theta 2 changing as the player touches the base? So now I'm going to use my change because it's asking me at what rate these are changing that I solved for. But what I'm interested in now is my x is approaching 0. Remember what x is. X is how far he is from second base. Well, if he's sliding into second base, when he reaches second base, my x value is 0. So I'm taking a limit. It's not, because in this case, I'm going to just go back. Okay, these are all the steps that we already. So I plugged in my xy over y dx dt, and I end up with this, my y squared. So I'm just doing the same thing. I'm just plugging in all my pieces here. And so now when I plug in my change, my rate of change here, my negative 16, the only thing I see is, well, but there's still a variable here. But I'm going to take the limit as x goes to 0, so I'm just going to let that be 0. That's why I said this is an easy limit. You can automatically plug that in and get your answer. Okay, so all you're doing different with this one is your rate of change changed here, okay, from the negative 18, because that was him running, to now he's sliding, and then we're leaving x alone. We're just going through all the steps because then we're going to take the limit of our x as x goes to 0 and get our answer. Once again, do the same thing with theta 2. So, I mean, think about this. It took us, 15 minutes, to get through this in class, and I went really, really fast, right? So if you had to work this, which you do for homework, it's just difficult for me to do that under test conditions. So this ends chapter 3. Now we're moving on. So